So, topic of our today's lesson is contemporary orthodontic archwires. There are shown possibilities of contemporary orthodontic archwires like high flexibility. Content of our today's presentation: introduction, evolution, ideal properties of archwires, classification, clinical considerations, and advances in archwires. Introduction. Over the last century, material science has made rapid progress. Not only have the materials, but also the philosophies have changed. Wires which had increased resilience and low cost were favored. Hence, stainless steel prevailed over the noble metal alloys. The appliance philosophies and material science progress is closely interrelated. All the wires that were introduced and never once have some very individualistic and unique properties with them. In order to use never wires, it's necessary to know the material properties. Active components of fixed archwire is active components of fixed appliance. Inherent capacity for elastic storage. Of applied forces. Bring about tooth movement through medium of bracket and buccal tubes. In the rational selection of wires, various factors to be considered. Evolution of archwire. The chronological development of archwires according article Orthodontic Product Update, British Journal of Orthodontics. First phase. Orthodontists used gold and stainless steel from beginning of 19th century till 1960s. Next phase. Stabilized nickel titanium archwires called stabilized martensitic. It is 70 years of last century. Third phase. Super elastic night-tie archwires called active orthodontic. 1970s. Fourth phase. Thermodynamic night-tie nickel titanium. Active martensitic. And now a great thermodynamic. Let's begin from gold. Up until 1930s, the only orthodontic wires available were made of gold and their alloys. In 1887, Apple tried replacing noble metals with gem and silver, called a new silver. The aesthetically pleasing, excellent corrosion resistance, and a low proportional limit. The material that was to truly replace noble metal was stainless steel. Now about terms. What does it mean? Orthodontic. According to the Free Dictionary, orthodontic means a non-magnetic solid solution of iron and another alloying element, usually assumed to be carbon unless otherwise specified, used in making corrosion-resistant steel. Once again, a non-magnetic solid solution of iron and another alloying element, usually assumed to be carbon unless otherwise specified, used in making corrosion-resistant steel. 1940s years. Beck with Wilcock introduced Australian stainless steel. By 1860s, gold was universally abandoned in favor of stainless steel. 1960s years. Cobalt chromium alloys were introduced. Their physical properties were very similar to stainless steel, but this alloy is softer and more formable. 1962 year. William Buchler was discovered nitinol. It is a special high flexible alloy at Naval Ordnance Laboratory, State Maryland, USA. Andreas and George and co-authors introduced nitinol in orthodontics in 1971. Please, colleagues, notice there were 9 years until discovering of this alloy and introducing in orthodontics in University of Iowa. The original alloy contained 55% of nickel and 54% titanium. The Unitec company licensed the patent and offered a stabilized martensitic alloy that doesn't exhibit shape memory effect under the name nitinol. And now orthodontists around the world use term nitinol. 1977 year. Beta titanium was introduced to orthodontics by Burston and John Goldberg. They are shown. Beta titanium alloy. Modulus of this alloy was close to that of traditional gold, but this alloy good spring back, good formability and good weldability. '84 year. Wilcock, as per request of Dr. Malin Hoyer of Melbourne, Australia, resulted in production of ultra-high tensile stainless steel round wires, called the Supreme Grade or Australian wire. 1986, Miura reported Japanese night eye. Developed at Fukuoka Electric Company, Japan, Chinese and Japanese night eye are active orthodontic alloys that form stress-induced martensite. Abbreviation: stress-induced martensite, SIM. What does it mean, martensite? Called by Adolf Martens, German metallurgist. Wilcock, 1988, much harder, alpha titanium. 1990, Neocent alloy introduced as true active martensitic alloy. Neocent alloy. 1992 was proposed OptiFlex Archwire by scientist Talas. It is a unique mechanical properties with high aesthetic appearance. They are shown this Archwire. As can you see, it's absolutely clear. 1994, Cooper nickel titanium was proposed by Dr. Rohit Sachdeva, shows phase transition, and was proposed few types of Cooper nickel titanium: 15 Celsius degree, 27, 35 and 40. What does it mean? It means that previously shape this Archwire will get with this or this or this or this temperature. Then in the millennium, titanium niobium was proposed, called gum metal, for tooth-to-tooth finishing. But now I'm working with this alloy for all treatment, not only for final stage. Classification of Archwires. Classification based on the material constituents. It is metallic or non-metallic. But based on the cross section, Archwires can be round, rectangular, coaxial, twisted, woven, according to material used. Archwire could be made from gold alloy, gold Archwire, stainless steel Archwire, chrome cobalt Archwire, nickel titanium Archwires, martensitic, austensitic, superelastic, Japanese nitai, Chinese nitai, beta titanium, TMA, alpha nitai. Then copper consistent nitine and ceramic or coated OptiFlex Archwire. Based on cross section, round Archwires are used like this one, are used at initial and intermediate stages of treatment to correct crowding, level the arc, close spaces. Rounded, rectangular, square or rectangular. So coaxial, they are shown Archwire from 5 parts, but there are 7, 8, 9 but coaxial Archwires, and twisted or woven. What about requirement of ideal Archwires? According Kasai, 1997, ideal Archwire must be aesthetic, must have low stiffness, high strength, high range, spring back, high formability, resiliency, coefficient of friction, biocompatibility and weldability. What about spring back, range of action? Will it deflect that far? Third point, strength. The highest amount of force delivered by the wire. And stiffness. It is spring rate, magnitude of force at a given deflection. Factors affect the force wire exerts. It is thickness, length, and material. About stiffness. Stiffness is proportional to the diameter of archwire. As can you see, like 0, initial point, is diameter 14, 0.14. But if we increase diameter near 70%, stiffness will increase more than 4 times. So conclusion, small increment in size will give us big increment in force. Width and height, shape, and you need to understand that stiffness of size 19 to 25 is more than stiffness of archwire with size 18 to 25. Stiffness is inversely proportional to length. If we will take archwire arch or metal length 6 mm and take it like 1, if we increase length in 2 times, stiffness will increase in 27 times. Stiffness is inversely proportional. Development of the high technology alloys. Nitride alloys were developed in the early 1960s for space program by Brunner in USA. This metal was called the memory metal. Very complex structure and mechanical behavior. Mechanical properties and thermal behavior are highly affected by composition, machining characteristics, and heat treatment during manufacturing. As can you see, this article was published in 1968. And you need to know about effect called shape memory effect, or SME abbreviation. And now short video.
This spring fascinates me. I'll completely uncoil it, except for a few kinks. This spring fascinates me. I'll completely uncoil it. Watch as I put it in hot water, 75 degrees or so. Rapidly, the spring reforms. Now, watch as I put it in hot water, 75 degrees or so. Rapidly, the spring reforms. Let's watch it again, but close up. I stretch the spring, and then, to slow down the action, use a hairdryer to heat it. This spring is made from nitinol wire. The name comes from the elements it contains and where it was discovered: nickel and titanium at the Naval Ordnance Lab. It's showing what's called the shape memory effect. A length of this wire was formed at very high temperatures into a spring. The shape setting occurs at temperatures above about 500 degrees Celsius and then cooled. Almost no matter how it's bent at room temperature, it returns to its original shape when heated at 75 degrees Celsius or so. So why does nitinol have this memory? The key is understanding how the atoms move in response to stretching and bending of a piece of nitinol. Typically, any metal, whether nitinol or not, is comprised of small grains that, depending on the material, are microns to nanometers across. And each grain is comprised of atoms arranged in a regular, repeating pattern. If this metal rod were held at the top and stretched, then the grains might elongate. You can do this because the atoms inside move a bit. Metal bonds can reform more easily than in nonmetals, and so the atoms slip, although it's a bit more complicated than applied here, which looks like spherical atoms rolling along each other. It involves defects in the crystal that allow the atoms to move only small amounts. In nitinol, though, generally the atoms don't slip. They accommodate the stresses from bending, stretching, compression, and so on in a different way, which produces the memory effect. Here's a simplified two-dimensional version of the atomic structure of nitinol, but one that captures the essence of why it has a temperature-dependent memory. The crystallites in the small grains have a nice, tidy, highly symmetric arrangement. The atoms sit on the corners of squares. At temperatures above 500 degrees Celsius or so, the nitinol can be shaped into whatever form is useful. For example, the spring I showed you earlier. When it cools, the crystal structure, the arrangement of the atoms, changes only slightly. Notice that it's very similar. All the atoms are connected in the same way, but the nice, tidy squares are now rhombuses. Notice that even though the atoms move a bit, the overall shape doesn't really change. So, for example, if you fashion a spring, it still looks like a spring. This doesn't seem very exciting. This structure has a unique property. It's composed of rhombuses that are mirror images. For example, notice the position of the atoms above and below this line aren't identical, but are reflections of each other. This is called twin structure. You could have all of the rhombuses oriented this way, or this way. As you can now see, when the nitinol cools, it forms equal amounts of these two orientations of rhombuses. One's oriented this way, and one's this way. What produces the memory effect in nitinol is that these two orientations can easily be changed from one to the other with very small motions of the atoms. For example, if I take the cooled nitinol and change its shape, some of the crystallites might experience a shear or force across the top. Notice that in response, the atoms move and change the ratio of the two types of rhombuses. In this example, they all change to one type. You could imagine that in response to different forces, that in a large enough crystal there would be hundreds of mixtures of these two rhombuses, and many, many more in a three-dimensional structure. But notice this. At all times, the atoms are connected in the same way as in the high-temperature phase, unlike in slip, where atoms can rearrange quite a bit more. So when the temperature is raised again, these rhombuses, no matter how they are distributed, return to tidy squares. The only structure that can result is the original structure, and so the nitinol reverts to the shape it had at high temperature. There are some clever uses for nitinol. For example, this device has fascinated me since childhood. It's a type of engine. Its construction is very simple, a large and small wheel, each grooved on their side, with a loop of nitinol wire that runs through the grooves and connects them. To make it run, I just contact the lower edge of the small bottom wheel with water, which I've heated again to 75 degrees Celsius. Then spin the top wheel a bit, and the device then runs on its own. It uses the temperature difference between the water and the air to power the engine. When I remove the water, the wheel stops spinning. This engine runs because this loop of nitinol wire was originally straight at a very high temperature, so as it's heated, it tries to straighten. To see how that causes the engine to operate, watch what happens as I contact the lower wheel with the heated water. I'll mark the position of the wire on the left with a yellow line. Then, when I start the wheel, the wire's distance from the initial position is much greater. It's hard to see, so I'll mark its position with a purple line. This happens because when the bottom wheel comes into contact with the hot water, the section of the wire highlighted here in orange is heated. If it were not in a loop, then the wire would be straight like this. But because it's in a loop, as it tries to straighten, it exerts a force on the wheel, which causes it to turn. Let's break this down. On the right, the air-cooled wire returns. It wraps onto the wheel. As the water heats the wire, it starts to straighten, but is restrained by being in a loop. This creates a force at this point on the wheel from this fulcrum, which is the last point of contact of the wire on the wheel. This generates a force about the center of the wheel, which is transmitted as torque and sets in motion the engine. Although a lot of nitinol-based engines were patented, often the practical uses of nitinol are not as a shape memory metal, but as a superelastic material. Let me show you. Compare nitinol wire to a piece of copper wire. If I move the copper wire a bit and let it go, it returns to its original position. That's an elastic deformation. But if I go too far, it doesn't return to its original shape. That's plastic deformation. Compare that to this piece of nitinol wire. It shows that elastic response for small deviations, but if I do that same extreme deformation and then let go, the wire returns to its original state, even oscillating for a while. If I bend the wire into multiple loops and then release it, it becomes straight. This superelasticity is closely related to the shape memory effect. Let's compare the two phenomena and look at what's happening at the atomic level. I start with shape memory. Here's a piece of nitinol wire that's been conditioned at 500 degrees Celsius or so to be straight. At that very high temperature, the crystal structure in the grains is those tidy, neat squares. As it's cooled to room temperature, the twin structure forms, the one with the equal number of left and right rhombuses, which you recall doesn't change the overall shape much. Then, when I deform the wire, the atoms in the crystallite shift in the grains to some unequal mixture of left and right rhombuses. There are hundreds of possibilities. When I heat it with a hairdryer, the tidy, neat squares return, and the wire becomes straight again. The tidy, neat squares return. And then as it returns to room temperature, the twin structure returns, the one with an equal number of both rhombuses. Now, let's look at a nitinol wire that showed superelasticity. It's been conditioned so that its crystal structure is these tidy, neat squares at room temperature. It would form the twin structure at minus 15 degrees Celsius, so a much lower temperature than the shape memory effect. When I apply an external force to the wire, the crystallites and the grains deform into the rhombuses, whatever mix of those would allow it to accommodate the reshaping. When I remove the force, then, because it's at room temperature, it returns to the tidy squares. Here's an example of a commercial device that uses superelastic nitinol. It's a cage-like metal tube called a stent that's used by a cardiologist. The doctor inserts it into a vessel or duct, here it's shown in a coronary artery, and it holds the walls in place. Because these are superelastic, watch this. I can severely deform it, and when I release it, it returns to its original shape. To use it, a cardiologist chooses a stent with a slightly larger diameter than the vessel wall. It's then crimped to a size smaller than the vessel, inserted, and allowed to expand. Because it's larger than the vessel's diameter, it keeps a force on the wall and resists compression. Nitinol's other commercial uses are in high-end products. Premium eyeglasses built from superelastic nitinol so they can be bent and twisted yet return to their original shape. And it's used in designs where reducing weight is critical. For example, in the 2014 Chevrolet Corvette, a nitinol device replaced a heavy motorized actuator to open and close a vent in the car's trunk. There are thousands of more uses for nitinol, and perhaps for other shape memory materials. For example, polymers that exhibit this phenomena are now in development. I'm Bill Hammack, the engineer guy. Polymers that exhibit this phenomena are now in development. I'm Bill Hammack, the engineer guy.
And next video.
That forms a solid-state compound exhibiting definite stoichiometry in ordered crystal structure. Meaning, neither is in an ordinary alloy in which constituents are randomly positioned in the crystal lattice. Rather, atoms, nickel and titanium have a very specific locations in the lattice. Neither alloy exists as two crystal structures, austenite and martensite. In neither alloys, austenite phase transforms into martensite phase, and martensite phase then transforms back to austenite phase. During the martensitic transformation, austenite distorts into martensite by moving atoms by less than 1 interatomic distance. Due to the diffusionless nature of transformation, no change in composition occurs. The transformation process may include an intermediate phase called R phase as other martensite candidate. Such transformation path is also known as two-step transformation. This reversible martensitic transformation is first-order diffusionless solid-solid transformation and can be induced by both applied stress and temperature variation. The austenitic phase is stable at high temperature and low stress, while martensitic phase is stable at low temperature and high stress. Because of this, two remarkable properties are found in nitide-alloys: thermoelasticity and superelasticity. The temperature-induced change in crystal structure is called thermoelasticity or shape memory, while the stress-induced change in crystal structure is called superelasticity, frequently described as pseudoelasticity, due to the non-linear stress-strain curve, which is not typical of elastic behavior. This is schematic representation of superelastic behavior of an orthodontic wire. Let's have a look at it stepwise. AB segment corresponds to initial elastic deformation of austenitic phase, which is stable at low stresses. Point B is the minimum stress for transformation of austenitic to martensitic phase. Segment BC corresponds to transformation of austenitic nidide phase to martensitic nidide phase. Typically at 10% strain, transformation is complete. Segment CD shows elastic deformation of martensitic phase, followed by segment DE corresponding to plastic deformation of martensitic phase, with failure occurring at point E. During unloading or deactivation, the sequence of events is reversed, with segment D-F corresponding to loss of elastic strain in martensitic nidide, followed by transformation back to austenitic nidide, and finally loss of elastic strain in austenitic nidide. Segment BC and FG correspond to stress-induced transformation. The loading path is not identical with the unloading one, corresponding to stress-strain hysteresis. I hope you enjoyed the video. Thanks for watching.
Let's again. Nitide transformation. High temperature. Austenite. Low temperature. martensite. Martensite come to austenite during heating, but austenite phase come to martensite during decreased temperature. In response to temperature variation, the crystal structure undergoes deformation in which the molecular arrangement is modified without a change of atomic composition. The schematically showed that processes. Heating, cooling, deformation. The same processes. This table shows properties of different phases. Austenite nitide has a cubic crystalline structure. Martensite nitide hexagonal. Different elastics models. Austenite nitide more elastic, but more yield strength. Martensite nitide is responsible for the lowering of the delivery force. Austenitic nitide is responsible for elasticity. Modulus of elasticity of austenitic nitide is 3-4 times than martensite nitide. Similar diagram. And development of nitai alloys. At first, stabilized martensitic nitinol, then active austenite superelastic nitai, then active martensite thermal wires, then cuprum nitai, development of cuprum nitai, stabilized martensitic nitinol composed of 55 nickel and 45 titanium, introduced to orthodontic by Dr. Andresen mid 1970s. No shape memory or superelasticity. Deformation occurring during processing. Suppressed. It is passive stabilized alloy. Diagram. Advantages: low stiffness, springy, and high continuous and linear force delivery. Superelastic nitai, Japanese or Chinese wires, developed by Burston and Miura. Active austenitic and room temperature. And don't change thermoelastic properties in oral cavity. Superelasticity occurs above TTR, wire initially austenitic, only stressed areas transform to martensite stress-induced martensitic transformation. Superelasticity only exists when both phases of metal are present. Delivery of forces will be lowered in the needed areas only, like on this diagram. Advantages of superelastic nitai Archwires: excellent spring back for 4 or 5 times of stainless steel, and content forces of a large wire deflection. Activation and deactivation. SE nitai wires. The slope of the graph threads with a slope 3 times that of nitinol. 2 mm deflection is necessary for the formation of SAM in austenitic wires. Austenitic alloys only behave superelastically in very severe crowding cases. There are shown effect of heat treatment of self-elastic nitai deformation, of nitai deformation. Thermal wires, martensitic active. For the memory property to be clinically detectable, austenitic phase has to be slightly below oral temperature. For every 150 ppm variation in composition at 1 Celsius degree change in TJ occurs. Mainly martensitic at room temperature, softic, ductile with shape memory. This tool called polar bear. This tool is cooling into fridge and then touch to the elastic Archwire. But disadvantages of thermal wires: they are more expensive, very sensitive to manufacturing process, offer little advantages in a small diameter, may give almost no force in the unloading curve if they are not formulated correctly, so may be inefficient. very sensitive to temperature changes in the oral cavity. When we put thermal active night-eye archwires by our patient, we need to tell them don't eat ice cream, don't drink very cold drinks. They are shown effect of temperature changes on thermal archwires during activation. During cooling, loading is decreased very much. And of course, the happening effect of deactivation. And in case of a repeated short-term exposure to ice cream on torsional stiffness of thermal archwires, we will get decreasing of effectiveness. Next stage of development, copper night-eye. The addition of copper increases strength, reduces energy loss, and allows greater control of TTR. Long force Plato, better manufacturing consistency, tolerate repeated loading better, and 3 types of temperatures, 27, 35 and 40 Celsius degrees, like here. Uh, 27 degrees, superelastic archwire in patients with average or high pain threshold, normal periodontal health, and where a rapid tooth movement is required. 35 degrees, thermoelastic wire in patient with low to normal pain threshold, normal to compromised periodontal health, where relative low forces are required, and 40 Celsius degrees, thermoelastic wire in patients who are sensitive to pain with compromised periodontal conditions, good as initial rectangular wire. Next stage of development, night-eye archwires, graded thermodynamic night-eye archwires deliver different amount of force at different areas of the dentition according to the surface area of periodontium, controlled by specifying different TTR, 80 grams of force anteriorly and 300 grams posteriorly. Beta titanium alloy, TMA, titan molybdenum alloy. Medium stiffness, produce gentler linear forces than stainless steel, has more range and greater spring back, has a rough surface. The diagram with comparison of different stiffness with different materials of archwire: stainless steel, cobalt chromium, titan molybdenum and nickel titanium. Application of archwires: aligning arches, working arches and finishing arches. And step by step, we need more stiffness but less range. The table is showing spring back and stiffness ratios of different materials. Like initial point was given stainless steel, but spring back of another alloys will decrease. Multi-strand stainless steel from 1.5 to 2 in comparison with traditional stainless steel. Beta titanium more springly, nitinol more, and super elastic niti the most. But stiffness will decrease, as can you see. First stage aligning wires need have low stiffness, low forces on activation, high strengths, prevent permanent deformation, and a long working range, maximize activation. Now about clinical considerations. First, aligning wire, which is the best. For initial stage of orthodontic treatment would be the best size 0.15 multi-strand stainless steel or 0.12 super elastic niti or next Archwires. But we need to remember about physiological force. We can compare in this table amount of force delivered by wires. The most force is delivered by size tradition nitinol 16 to 25 300 grams, but the minimum multi-strand stainless steel wires. Advantages of niti as aligning Archwires compared to multi-strand stainless steel: a long working range, damage resistance, sustained forces, and low forces. About aligning Archwires, the smallest diameter Archwire to be avoided as at this stage. Small amount of force play between bracket and wires limits the accuracy of alignment produced. An efficient Archwires progression. Multiple round and rectangular wires, for example, 12, 14, 16, 18, 16, 22, 18, 25. Evidence-based Archwire selection. Many scientists compare different properties of different Archwires and have got different results. Results of clinical trials. Rates of tooth movement hardly affected by type of wire. Any difference not clinically significant. Pain experience not affected. Results are related to the individual variations in metabolic response within the periodontal ligament and bone. Archwire sequence. Three randomly allocated Archwire sequence in terms of efficiency, patient discomfort, root resorption was compared. A. 16 niti, 18 to 25 niti, quantity of patients 41. Next one, group B, 16 niti, 16 stainless steel, 20 stainless steel, quantity of patients 44. And group C was used Archwires 16 to 22 Cooper niti, 19 to 25 Cooper niti, quantity of patients 44. The endpoint was the passive placement of 90 to 25 stainless steel for at least 4 weeks. Results of this trial. No statistic difference for patient discomfort at hours 4, 24, 3 days and 1 week. Root resorption was not statistically significant with average root resorption between 0.96 to 1.39 millimeter. The table is showing time required to reach the working archwire. As can you see, the less quantity of visits they are shown in a group A. Can thermal rectangular wires be used as first alignment wires? We know that first alignment wires, as usual, used 15 multi-strand stainless steel, 14 night tie, 18 thermal night tie, and 20 to 20 copper tie, with moderate crowding. 60 thermal, 14 super elastic thermal night tie, and in patient with severe crowding, we need to use 14 thermal or 12 super elastic tie. When we need to move to the next wire, when the next wire can be engaged in all the slots, look at the worst tools to decide, watch for rotation particularly, give enough time for the wire to work, especially second aligning wires, 18 to 25 night tie and 20 to 25 copper night tie. Possible uses of 20 to 20 copper night tie. Final alignment wire after round night tie wire. Sole aligning wire for mild irregularities. Realignment after bracket repairs or repositioning. Next step of treatment, stainless steel working arches. What we will get from stainless steel working arches? High stiffness and, as a result, good control. These archwires are easily adjusted with low friction, can be welded or soldered, and very cheap. But night tie working arches, flexible, poor control, difficult to adjust, higher friction, cannot weld or solder, and more expensive. And finishing archwires. Options for choose fitting archwires. For 22 slot, it is size 21 to 25. Steel too stiff, night tie not adjustable, poor torquing, better titanium, ideal stiffness used to provide root paralleling. But the most effective using of properties archwires we can get with self-ligating brackets. In self-ligating brackets, we will get low force and low friction, but with active ligation, we will get high force and high friction. They are shown why we will get less effective torque control in case of in comparison with conventional or active ligation. What about self-ligating brackets? Friction is increased in 5 times over diamond if using a conventional bracket with steel ligages. Frequency is increased in 1,500% over diamond if using an elastic ligature. There's 70 grams of frictional force per tooth when using an elastic ligature. This diagram is showing that investigation. What advantages of self-ligating? Brackets. High technology wires should be used. Smaller dimensions. For example, we can start with 14 size of Archwire. Give 10 weeks appointment interval instead of traditional 4 weeks appointment interval. Use 14 to 25 Kupernetai second aligning wires to correct rotations. Then 18 to 25 Kupernetai to express additional torque. But many scientists are believed that future is for fiber reinforced composite arch wires. And at the end, I would like to advise you throughout a few very interesting articles about arch wires or this research.
So you can send it, Professor?
Yes, it is finish of our lecture. As for me, this article would be very interesting for you too. Systematic review.
Okay, that's